operators get used to derive other quantum mechanical operators. So, actually, that's new. You haven't heard that before. It's not really, doesn't really belong to a summary. Okay. Now the fourth one. In general, you have a wave function, a state function, a state vector, a ket. A lot of labels. Now, if you're going to measure a particular observable, A, whatever it is, then A, that observable A will have its corresponding operator A hat, there will be corresponding eigenfunctions and eigenvalues for that operator, for operator A hat. So before the measurement, you can expand this general wave function here in terms of these eigenfunctions. And these eigenfunctions are orthonormal, right? They're orthogonal and they're normalized. So bracket phi n will give you 1. Okay? Bracket of phi I, phi j will be 0 if I and j are different. Okay? So they're orthonormal. So here's your eigen equation, very general, for observable A, or A hat. Here are the eigenfunctions for that observable operator, and here are the eigenvalues. So that's your general eigen equation. So you've seen that before. So these eigenfunctions here are a complete orthonormal set. They're a basis in the mathematical sense. Complete in the sense they are sufficient to approximate, well, even better, any general function using a weighted sum of these basis states. So you can express any vector, any state, in terms of these eigenfunctions, in terms of this complete orthonormal set of functions, or this basis. That's what a basis is. It's a complete set that, in terms of which any general vector, if you like, can be expressed in terms of a weighted sum. Right. So that's the state before the measurement. You perform the measurement on observable A. This wave function will collapse, as I was saying a bit earlier, to one of these eigenstates, let's say phi n, with the corresponding eigenvalue, lambda n. That lambda n will be the measured value that you get. You're trying to measure some physical quantity. What's the energy level? What's the angular momentum? What's the momentum? Whatever. You're measuring it, and the value you'll get will be one of these eigenvalues. Right? That's basic to quantum mechanics. Right? And the probability that you get this eigenvalue, that this result of the measurement, will be this coefficient, the corresponding coefficient for phi n. In other words, Cn, and you square it to get the actual probability of getting that measurement result. Okay? Now, given those, these postulates, you can then calculate the average value that you'll get, because we're talking quantum mechanics, right? Statistics. No determinism, according to the pretty well standard Copenhagen interpretation, the Bohr, B-O-H-R, school of thought. I dare say most physicists tend not to think philosophically about the interpretation of their work, but for those who do, it's hotly contested. I've said that many times. Anyway, so given the statistical nature of the conventional interpretation of quantum mechanics, the average value that you'll measure, you can calculate from the bra operator ket formalism, and three bars, so by definition defined. Here's using this expression, and you plug in the corresponding operator for the observable that you're talking about, A, right? And this will give you the average measured value for that observable A. Alright, what else does it say? The notion of compatible observables. Compatible meaning that you can measure both observables, A and B, to infinite accuracy simultaneously. Right? If you measure one, it does not disturb the other, vice versa. Okay? And if two observables are compatible, then they have the same eigenstates, the same set here of these. They share the same. So you'll have different operators, like A hat and B hat, but their eigenfunctions will be the same. And hence the commutator is 0. Those two operators, A hat and B hat, commute. Alright, well, that's it for the theory, chapter 6, long chapter. Now with all this stuff that you've now got under your belt, hopefully, you now have powerful tools that you can use, say in chemistry, like quantum chemistry. You can start analyzing, for example, the nature of the chemical bond. Why do two atoms share electrons to create a chemical bond? Well, you now have enough tools in quantum mechanics to be able to analyze that phenomenon of the chemical bond, which is basic to human existence, of course. We need molecules. And chemistry is the study of molecules, effectively. There's similar phenomena. Well, atomic physics is pretty well where quantum mechanics came from. Nuclear physics. In a sense, the solar system model of the atom is to some extent reproduced inside the nucleus. You have the nucleons, the protons and the neutrons. They too have layers, energy levels of n, principal quantum number n, the energy levels. Analyzing the behavior of nuclear phenomena also uses quantum mechanics. Molecular, well, it's sort of chemistry, behavior of molecules and so forth. And solid state physics, I have to talk about that much. Solid state physics, well, you just guess from the name, solid. So it's talking about crystals and stuff like that. Physical phenomena that are not in gas form or liquid form, more in solid form. So the behavior of, for example, silicon transistors. Like the analysis of the behavior of the transistor required quantum mechanics. So the biggest industry with all its spin-offs now, I think, is the silicon computing, telecom and so on. All those huge industries that are based on the behavior of the transistor, all that came out of quantum mechanics, right? Because the behavior of the transistor is a quantum mechanical phenomenon. So to understand it, you need quantum mechanics. So quantum mechanics already, long ago, has lost its ivory tower type reputation at the beginning. It's now hugely valuable. Right? It's worth trillions of dollars a year. That's the nature, the economic nature of quantum mechanics. Next lecture on the theory side. I've yet to do the problem solving for sessions for this lecture, but the next theory session will be on chapter 7 on angular momentum and spin. So stop there.